Hello everyone, my name is Liang Qian. I'm a master student at Harbin Institute of Technology, Shenzhen. The paper I'm presenting today is titled Chunk-Aware Alignment and Lexical Constraint for Visual Entailment with Natural Language Explanations. Visual entailment with natural language explanations aims to infer the relationship between a text-image pair. Usually they are entailment, neutral, and contradiction, and then generate a sentence to explain the decision-making process. For example, giving an image premise that a boy is sitting on a step, and the text hypothesis, an Asian youth is doing a skateboard trick. The model needs to figure out that the relationship is contradiction and generate the explanation. Sitting and doing a skateboard trick is not the same. Typical methods usually use a token-level vision language model to infer the relationship, and then the joint vision language representation along with the answer will be fed into the generator for an explanation. However, such methods suffer from two problems. First, most vision language models focus on building token-level alignment to learn the joint representation, neglecting the high-level semantic alignment between the phrase and image region. It often leads to ambiguous semantic understanding and vague alignment, making the classifier error-prone. For example, as shown in below, although they align the words such as use, doing, skateboard to different image regions, the discrete token-level alignments cannot capture that the chunk is doing a skateboard trick, actually describes an action. The misinterpretation of the chunk leads to the incorrect alignment of doing and trick, and results in wrong inference result. Secondly, the above methods generate explanations by solely applying attention to the joint representation, neglecting the critical decision-making points of relation inference. Thus, the explanation is usually confined to limited words. For example, it only attends to Asian use and is irrelevant to the second half of the input. To tackle the two problems, we propose a chunk-aware alignment and lexical constraint-based method, which can align the text chunks to image regions to infer the relation, and then generate explanations that is centered around the words of the inference process. Our method mainly contains three modules. To build better cross-model alignment, we utilize a chunk-aware semantic interactor to learn within chunk, cross-chunk, and cross-model semantics. And then, to obtain accurate relationships, we utilize a relation inferer to conduct fine-grained inference on the combined outputs of the chunk-aware semantic interactor and the pre-trained vision language model. Then, to generate faithful explanations, we utilize a lexical constraint-aware generator to incorporate the keywords during inference into explanation. And here is the overall architecture of our method. First is the chunk-aware semantic interactor. It contains three interactors of different level to capture different semantics. The within chunk semantic interactor to exploit the rich semantics contained in chunks. The cross-chunk semantic interactor to incorporate the global information into each token. And then the cross-model semantic interactor to build vision language alignment on chunk level. Then the relation inference combines the outputs of chunk-aware semantic interactor and pre-trained vision language model to obtain a comprehensive representation. Then it utilizes attention mechanism to conduct fine-grained inference. Last, the lexical constraint-aware generator is used to generate explanations that is faithful to the inference process. First, we calculate the initial generation probability via a transformer-based language model. Then we construct a word set as the lexical constraint via the attention score of the relation inference, which can be seen as the keywords during inference. We assume that if the attention score of the word is higher than the median, then the word is important during the inference process, and the explanation should have higher probability to contain the word. Based on the word set, we can obtain the lexical constraint probability by calculating the probability distribution of the tokens within the set. Last, we combine the two probability to obtain the final generation probability. For training and inference, we first pre-train the chunk-aware semantic interactor to improve the accuracy of semantic vision language alignments. And then we use the training pipeline for the whole model. First, we train chunk-aware semantic interactor and relation inference for relation inference. Then we freeze their parameters and train the lexical constraint-aware generator for explanation generation. During inference, we also adopt constraint bin sample for generation. Conventional bin sample score each bin with a generation probability, which ignores the faithfulness of the generated explanations. To alleviate this problem, we propose a constraint bin sample that scores each bin with the probability and the number of the occurrence of the constraint words. We compare our proposed method against 5 strong methods on 3 datasets. We use 3 evaluation scores, ST, SE, and SO. ST represents the inference accuracy. SE represents the average natural language generation score of explanations that are inferred correctly, and SO represents the overall performance. We can see that our method achieves the best performance, substantially surpassing all the baseline, and the ablation study also verifies the effectiveness of our method. We notice that the lexical constraint-aware generator has a more significant influence than the constraint bin sample. The two components act at different but complementary points. The relation inference can better incorporate the fine-grained alignment on different levels, and the influence of the chunk-aware semantic interactor is the most obvious. Here are some case studies. The same color shows the alignment between the chunks and the image regions, and the bold words are the lexical constraint. In the first image, we show an example with the inference results and explanations of each model. Our method is the only one that infers the correct relation and generates a faithful explanation. In contrast, other models mistake the objects and predict the wrong answer or generate a pointless explanation. In the last 3 images, we show some qualitative results from our model on 3 datasets. We observe that although we only provide alignment for non-chunks during pre-training, our method can learn alignment for other part of speech chunks, such as is given during fine-tune, which may be benefit from the cross-chunk semantic interactor. In conclusion, we propose a unified chunk-aware alignment and lexical constraint-based method for visual entailment with natural language explanations, and we build chunk-aware cross-model semantic alignment. Also, we incorporate the keywords of the inference into explanation to enhance the faithfulness. The future works may be build alignments between chunks and visual concepts, rather than predetermined regions, and improve the relevance between explanations and input image. That's all. Thanks for your time.